But I promise it's not. One of my favorite subjects in school was physiology. As a chiropractor, I couldn't even tell you how many physiology classes I took. But what I'm trying to do is I'm trying to set up a conversation about action potentials, about understanding how the nervous system works. And to do that, we got to start at the beginning. And that starts with membrane potential. This could seem a little, like I said, a little intimidating, but I promise you, if I can learn it, you can learn it. I'm gonna try to explain it as simple as possible. I promise. So, I don't know if you guys can see this little laser. Okay, perfect. You can see the laser. Before I get into what makes a membrane potential, I feel like I have to define a membrane potential. And essentially, it's a charge difference. And I'm not talking about like, you plug, I'm not saying, you plug your phone charger into a socket, you charge your phone. What I'm talking about is the difference of charge, I guess you could, in terms of millivolts, yeah, an electrical charge on either side of a membrane. Now, for those who don't know what a membrane is, the easiest way for me to explain that is this. If we're talking about a fiber of something right here, let's just say a nerve fiber, because nerves are made up of fibers. I like to imagine it as kind of a tube. And so in order to make the tube, there's an inside of the tube and there's an outside of the tube. And what I'm talking about in terms of membrane potential is the charge difference on either side, positive or negative, positive or negative. Now, the charge difference is made by a lot of different things, right? But mainly what I'm talking about is the electrochemical charge, and that's the exchanging of ions, cations and anions. So cations being positive and anions being negative. Now, three main things go into creating this charge difference, this membrane potential on either side. Honestly, listen, there's more than three, but I'm gonna go into the main three, okay? Number one, if you look down here, if you can see something called a sodium-potassium pump, sodium-potassium ATPase. Let me kind of zoom in on this a bit. So imagine there's a membrane right here. See all these little lines right there, and then one on one side, one on the other. This is the membrane. Right here is the inside, and right here is the outside of the membrane. Kind of correlates with this. Right here's the inside, right here's the outside. Perfect. So on this membrane, we have something called a sodium-potassium pump. And this pump creates a concentration gradient. So a concentration gradient is essentially there's more of something on this side than there is on this side. And for our conversation, we're gonna be talking about sodium and potassium. Now, the ATPase, or the sodium-potassium pump, what it does is it takes sodium from inside and pumps it out, and it takes potassium from outside and pumps it in. And if you see right here, there's this little star that says ATP. That's like, the way that I like to think of it is like we have a big fan here, and then in order to work this fan, you have to put a coin and you got to put a quarter in. And each time you put a quarter in, it moves this fan and it pumps things out and it pumps things in. So for our purposes, the sodium-potassium pump is run by ATP because we need energy, we need money to push something out and bring something in. Now, if you see here, we're taking 3 sodiums out of the inside of the membrane and we're pumping 3 out. And then we're taking 2 potassiums from outside and then bringing those in. If you'll notice, you'll take a second and kind of think about that. What you'll see is that if we're taking 3 positives out and pumping 2 positives in, what that means is we have a net deficit of 1. That makes sense. So this sodium ATPase makes the inside of the membrane right here a bit more negative. Just a bit, not much, because you see what we're doing is we're pushing sodium out and putting potassium in. And it's just a difference of 1. However, what that does is it creates a concentration gradient, meaning we're pumping sodium in, so there's gonna be, it's gonna be unbelievable. There's gonna be a lot of potassium in here, and there's gonna be quite a bit of sodium out here. That's one part, one thing that is contributing to the membrane potential, the charge difference. Now, another thing, there are a couple more things, but you see right here, this says a potassium leak channel. Mainly what that means is, since there's going to be a lot of potassium in here, right? Because of the ATPase, because of the concentration gradient, there's going to be a channel that's going to allow the potassium to leak out. In terms of how that makes the membrane potential, we're talking about the diffusion rate. So potassium, since there's going to be so much in here, is going to be willing and easily able to diffuse outside, right? And you also have to consider this membrane right here has something called permeability. Permeability means, I'm trying to think of the easiest way to explain this. Permeability is the likelihood that something is going to move through. So if this right here is permeable, or I guess the word would be passable, you could kind of, interchange those. If it's permeable, then it's going to allow something to go through, right? This membrane right here and this membrane right here are really permeable to potassium. It's going to allow potassium to come in and out pretty easily. And honestly, that's the diffusion rate that goes along with the membrane. So that's another thing. So far we've talked about sodium potassium pump, and we've talked about the potassium leak channel. There's another piece of the puzzle that is going to come into the equation, and that's the rate at which sodium diffuses through this membrane. So just like potassium is going to come out here, sodium is also going to come from out here and come inside. So here's the inside and here's the outside. Now, if you think about it, what we have is a concentration gradient set up by the sodium potassium pump, causing more potassium to be in here and more sodium to be out here. We have potassium leaking out because there's so much potassium in here, not a whole lot out here, and then we have a lot of sodium out here, not a whole lot of sodium in here. So what's going to happen is, kind of to set up this story, is we have sodium coming in through the membrane, obviously through a channel. We have potassium exiting the membrane through a channel, and we have the sodium potassium pump creating a concentration gradient, and we need ATP to do that. Now, the reason that, let me also add this. The inside of a nerve, the membrane potential is essentially negative, right? And that's because of all these contributing factors: sodium potassium pump, potassium leak channel, and then we have the diffusion potential of sodium. But if you look right here, this sodium potassium pump, this potassium leak channel and the diffusion potential of potassium, this is really what makes the inside of a nerve, the membrane potential, so negative. And it's because potassium is bound to a cation. It's bound to it's bound to negativity. It's bound to an anion. And what happens is, in order for this potassium to leave, it has to separate from that negativity. And so what happens is, we'll have some positivity going out here, and we'll have a negative ion out here. And so what happens is, if we have potassium, since the concentration gradient is so high out here, we have potassium leaving, what's going to happen is you're just going to have a lot of negative anions out here. And so what we have is, we have the concentration gradient so high here, potassium leaving, and then we have a bunch of negative anions out here, and then we have a lot of positivity out here because of the sodium potassium pump. And then you also have to consider the diffusion potential, which, this membrane right here, and I know I might be speaking a lot, and I hope this is making sense to you guys, is so permeable to potassium. I mean, it's unbelievable, especially compared to sodium. And honestly, it's like 100 times more permeable to potassium. I mean, if we have so much potassium here, a lot of sodium out here, potassium easily leaks out, and then sodium cannot really come back in all that well. I mean, you're gonna have a negative membrane potential out here, a negative charge difference out here. Now, let me set up this conversation again. The inside of the membrane, due to all these factors, we're gonna have, I guess, a ratio of sodium 10 to 1. So for every 10 sodiums, we have 1 sodium inside the membrane. So for every 10 sodium outside, we have 1 sodium inside. And that's due, once again, to this sodium-potassium pump and the diffusion rate. For every 35 sodium, or for every 35 potassium that we have inside the membrane, we have 1 potassium outside the membrane. So this pump really is doing a lot of work. This leak channel really is doing a lot of work. And then we also have just the diffusion rate of sodium and potassium doing a lot of work to make the charge overall negative inside and positive on the outside. So that sets up the membrane potential, the charge difference. Now, I need to also say this. We need to talk about the difference in membrane potential of different types of cells. So this is a chart that came out of one of my favorite textbook, Guyton Hall Physiology. Neurons, skeletal muscle, smooth muscle, cardiac, hair, astrocytes, erythrocytes, photoreceptors. Membrane potential, the charge difference, is going to be different between cells. What I'm talking about right now is a neuron. So a nervous tissue. If we're talking about that, what you're going to see is that roughly a membrane, the resting membrane potential for a neuron is going to be roughly about negative 70. We're just going to say negative 70 millivolts. And that sets up a conversation for what we call graded potentials and action potentials. But for now, I want to stick with just this. So understanding that resting membrane potential, just membrane potential, is set up by a couple different things, mainly sodium-potassium pump, diffusion potential of potassium going out, and then the diffusion potential of sodium coming in. Now, I like to tell stories, and hopefully this story is going to make sense. So, consider this. I always like to think. For me, this is like a home, right? We have inside the home and we have outside the home. I go home. I work all day. And what I'm doing is I'm trying to make sure that my house has peace. I'm trying to make sure there's some sort of homeostasis inside the house. And I'm working and I'm going home and I'm paying my bills. And what I'm doing is I'm trying to make sure that the internal environment stays pretty consistent. And so what happens is I'm paying the bills right here. I'm paying money into the sodium potassium pump to make sure my inside stays pretty consistent. So the sodium potassium pump, my bills, I'm trying to make sure that my AC stays on, my electricity stays on, et cetera, et cetera. What happens is my environment is good. It's nice. I have just a little bit of a deficit. Now, here come my kids. And my kids, they open my doors, they let all the AC out, they're throwing money away. And that's what's happened here. That's what's they're throwing all my money, all the positivity's going out. And so what happens is, with this leak channel, I get a bigger deficit, a bit bigger of a deficit. And then what happens here is I try to supplement my income and bring in a little bit more positivity, but that positivity, that sodium channel, that sodium diffusion rate it doesn't impact my environment like I would like. And so what you see here is that we have, if this door is being left open, my AC's running out, I'm gonna be losing money. It's gonna be pretty negative in here. So that's just my little story. I like to set up a bit of a conversation just around membrane potential. And hopefully that leads us into another conversation of action potential and graded potential. Guys, thank you so much for hopping on the live. I appreciate it. Thank you for showing support. If you like this video, give a like. If you feel like it, you can subscribe as well. But once again, I'm just trying to make this an easy conversation for people. Membrane potential. Thank you so much, and I will see you guys later.